Hi everyone, my name is Katherine, and in this video, we will demonstrate how our adaptation of the OctoPocus guide to VR is not only feasible but also beneficial. In VR, buttons and menus are still predominantly used today due to user familiarity with pointing and clicking. However, they occupy space and do not facilitate expert performance. Gestures, on the other hand, can be performed in the 3D space around the user and increase the input vocabulary. But because they are not self-revealing, users need to explicitly discover, learn, and memorize them. One solution is to use a guide. A guide can be static, like crib sheet or cheat sheet, that displays what can be done and what the result will be. Or a guide can be dynamic like OctoPocus, which filters feed-forward options based on a partially performed gesture. OctoPocus also provides a continuous feedback by dynamically rendering the line thickness of each path, such that less likely paths get thinner and eventually disappear, while the most likely ones remain. The relevant literature would be that by Delamere et al. They use a Kinect for 3 degrees of freedom indirect input, a mouse for delimiting gesture, and a 2D desktop monitor to render 3D guides. Their primary investigation is on how feedback and feed-forward visualizations affect speed and accuracy of 3D movement. In comparison to our work, we focus on the VR context, which is fundamentally different in terms of rendering and input. Delamere et al. Also based their comparison against a video crib sheet in a 4-person preliminary study. But it remains unclear if a video crib sheet is any better than the static one tested by Bow and McKay. Thus, we chose to implement a VR-adapted crib sheet for the baseline in our study. In addition, we measured not only speed and accuracy, but also learning, recall, and usage rates. Despite all these differences, we adopted one of their key contributions to reduce visual complexity. In other words, our work focuses on replicating Bow and McKay's evaluation of both static and dynamic guides for the VR context. In our implementation of OctoPocus, pressing the trigger button and pausing for a moment reveals a rendering of all gesture paths. As the user starts moving in a direction, gestures that are less likely fade away. Eventually, this filters out all gestures except the desired one, and they finish drawing the gesture by releasing the trigger. Pressing the grip button enters an exploration mode where they can rotate and translate the entire guide to gain a better perspective to the 3D gesture space. This exploration mode can be activated at any time while viewing the standard guide. For crib sheet, pressing the grip button reveals a static 3D rendering of each individual gesture arrayed in a grid. This can also be rotated and translated, and once the desired gesture is located, the sheet is dismissed by releasing the grip button, and the gesture is drawn using the trigger button. Both OctoPocus and crib sheet were tested using gesture training and testing tasks. Each task trial begins by touching a start sphere, then a target gesture label appears and they draw the gesture. The trial ends when they see the label of the recognized gesture. The task is the same for both training and the test. The main difference is that during tests, no guide is available, while during training, guide is available, but it is not compulsory to use the guide. If they choose to do so, the trial is marked as novice, otherwise it is marked as expert. Overall, we follow Bow and McKay's general procedure where only 8 out of the 16 available gestures were trained and tested. The test follows immediately after each training, and together this forms one block. We had a total of 3 blocks to form the main phase. The main phase is sandwiched between a pre-test and post-test. During pre-test, each of the 16 gestures were presented in a different order and with no guide provided. Participants were instructed to provide their best guess. This is to measure baseline recall performance without any prior knowledge. All 16 gestures were also tested in the post-test. The main difference is that half of them had been practiced in the main phase and the other half had not. This is to measure incidental learning. We analyzed our time measures for novice trials. Overall, OctoPocus performs better in terms of input time but worse in terms of reaction time. For accuracy, OctoPocus is more accurate than CryptSheet for all three measures. In terms of learning, both guides help participants to recall more gestures after each training block at B1, B2, and B3, and also similar performance in terms of gestures they were not explicitly trained on. Both Bo and McKay's and our results show that OctoPocus is more accurate than CryptSheet. However, differences lie in terms of reaction and input time. This could be due to the extra dimension of 3D gestures that make it harder to execute and learn as compared to 2D gestures. Although our design is very different from Delamere et al. Study, we can still make meaningful comparisons. In terms of trial duration, our guides are faster by 36 percentage points, while our gesture recognition is more accurate by 20 percentage points. This suggests reliability in our algorithm implemented. For more detailed descriptions and discussions, please refer to our full paper. Thank you.